Hello, everyone, and welcome to episode 98 of the Hyperthesis podcast. I'm Patrick.
I'm Feely.
And I'm Liam.
Well, as you can hear, we are breaking from our trends a little bit because we don't have a guest on today. We are going with a kind of more traditional episode, I'll call it, where we're just talking about some topics in science that we've come across. So we'll be going over that kind of thing today, and maybe we'll have a guest for the next episode. Maybe we won't, but stick around for this episode to hear some interesting facts from squeaking sand to spectroscopy and anything in between there. So, to start, do we have any intro topics?
The squeaking sand intro topic that you just mentioned.
Oh.
Yes.
What's that?
So it's sand that squeaks, it turns out. I don't really remember how or when or where, but at some point in the last few weeks, I became made aware of this naturally occurring phenomenon known as squeaking sand. So this can happen on certain beaches around the world. Where when you walk through the sand, it produces this audible squeaking noise. So basically the action of your foot like kicking the sand or scuffing the sand or disturbing it. And if you've ever walked through sand before, you know that's typically not what happens. When you walk through sand, maybe it makes a tiny bit of noise, but you normally don't hear much. So it's kind of like, I imagine it would be pretty jarring to walk through sand and it squeaks at you, and it's fairly loud. And depending on the sand, it can like bark or scream or whistle, which is kind of weird. So it's this naturally occurring phenomenon that we kind of have a qualitative understanding of, but it's interesting, we don't have a very good quantitative understanding of it yet. So that's why I kind of chose to talk about it. And it only happens under very specific conditions. My guess as to why we don't have a quantitative understanding of it is probably because it's this, imagine you're a scientist and you're applying for a grant or you want some money. You're probably not going to get a lot of money or attention from others to describe something like this, opposed if you go and, revolutionize quantum computing or something along those lines.
That being said, just on that topic, it's interesting, to see what funding is being provided and the knock-on effects of that. So just as a very quick example, research into I believe it's a type of reptile known as the gilly monster, or the gilly, whatever it is, down in the United States, essentially set the foundation for the eventual production of Ozempic, which helps people with diabetes. It also has the side effect of helping people lose weight, but kind of this interesting medication that occurred just from unrelated research into the gilly monster. So just saying, fund whatever projects you can.
Well, but this also feels like there might be good applications for it because sand work in like granular scale, right? So the fact that granular material, when disturbed, produce specific type of noise. What else do we have that are granular scale in industry? Let's say you have a plant that use like sandblasting stuff, or you have anything that you cool in sand or heat in sand. Maybe there's something there. Well, I don't know what's the what do you call it? What the effect that Liam's got hopefully describe. Perhaps you have some understanding there.
Yeah, what do we know about the sand so far, Liam?
So it's been reported in a bunch of different places. So and for a long time, we know that the squeaking that occurs, or I like to call it barking. Maybe in this podcast we can get like a little audio clip of it and play it so people can hear it. I'll talk to Feely about that later. But if Feely, you and Patrick just go on like Wiki right now and type in singing sand, there's something else related to this called singing sand, which I want to talk about in another episode. But the squeaking sand, if you scroll down that Wiki page enough, there's a little audio recording of it and you can listen to it, and it's kind of funny sounding. So maybe we can play that here, but we'll figure that out later. But anyway, we understand. Oh, Patrick.
Sorry, I just want to say it kind of sounds like when you have like a guide wire that you kind of flick It almost sounds like that. Go check it out, but just I'm listening to it now, and
Like
it's very
dogs
like vroom,
bark.
vroom.
It sounds like barking to me.
Yeah, like for small dogs.
So it turns out that different kinds of sand will produce different sounds. Some of them can sound like whistling, some like singing, some like barking. So it depends on the properties of the sand. So we qualitatively we know that the output sound that you get from kicking the sand depends on the physical properties of the sand grain. It happens the most when the grains are small and very close to the same size. So most often when the sand is between zero point 0.1 to 0.5 millimeters in diameter, and when the sand contains a lot of silica, so things like quartz. It also happens when the grains of sand are very smooth, which is why. So if you get like a bunch of quartz grains that are close to the same size, this quartz is very smooth, and there's a whole science as to how you can get beaches with lots of quartz on them. It has to do with glaciers and things like that, and the Earth's dynamics when these continents formed, which I know nothing about.
Talking about very smooth thing. I remember not looking into, found some info on why soccer balls or football balls, and the spherical ones, are made to have groove and stuff, because they used to try to make it like perfectly round, right? Like smooth ball, like a pool ball. But apparently, that's really bad for aerodynamics. You get this kind of knuckleball all the time because it's too smooth that air doesn't know where to go. So sometimes it's go this way, and sometimes it go that way. But having this groove in the ball actually provide them like stable path aerodynamically to reach the goal, and it's much more predictable, because like if you have really smooth ball, you don't know where to go. It's just like sometimes small fluctuation will make it go this way. It's actually better to have grooves.
Yeah, there's a few instances where smooth spheres are not desired in sports. Like even like golf balls, right? They put these little dimples in them, and I think it basically reduces the I think it creates some turbulence, and it either creates a little bit of turbulence, which helps keep the trajectory more stable, or it reduces. I can't quite remember. I used to
I think
know.
like more. I think you were looking for like vortices, right, instead of
Yeah, yeah.
turbulence.
Well,
Like
turbulence and vortices are definitely related, but yeah, exactly. You're right. It's more
like
so
little
vortices than turbulence.
little eddies or something like that,
Yeah,
right?
and they basically help keep its trajectory stable. I mean, a bit unrelated to this sand stuff, but um, I don't know. Maybe if the sand were perfect spheres, it wouldn't happen, and you need a little bit of roughness. It's not fully understood, but so like I was saying, the singing sand phenomenon occurs with sand grains when they're small and very close to the same size, when they contain a lot of silica, so these smooth things like quartz particles or crystals. It happens also when the sand is very dry, but not too dry. So that's interesting as well. And the mechanism is believed that when you step on the sand, it causes the grains to move about and compress and slide against each other so that they vibrate. And because they're all close to the same size, they resonate together and will produce enough sound that you can actually hear it. So we know that qualitatively the squeaking sand, it depends on the size of the grains, how much silica they contain. They have to be wet but not too wet, um, and they have to be smooth. So there was this really good YouTube video that I found that it's titled "I Thought This Was Fake," and it's by the YouTube channel known as Atomic Frontier, where he discusses this and he makes this analogy to glass marbles. So he has a handful of glass marbles, and he like kind of crushes them and rubs them together in his hand, and they make a noise. But then he soaks them in water, and they don't make noise. They become smooth. So it's thought that maybe for these sand particles, when they're covered in water, they slide off each other more, or with the sand particles, they could just like the sand grains, they stick together and don't rub together. And he also shows that when you have different size sand or different size glass marbles in your hand, they don't rub together as much or vibrate. So that might be another explanation as to why the singing sand doesn't occur when the sand is different size. Additionally, it's thought that when the sand is very small, it can more tightly pack together, so you get more rubbing and more vibration. So it's kind of neat how but it's also it's not fully understood. There's all kinds of things that can happen.
You gotta be careful. Tightly packed. What I would expect it to move less because it's tight, right?
Well,
So
when I say
if it's loose, it would be able to rub more, but if it's tight, it's actually more compact. So it won't be able to rub or have a lot of friction.
I guess maybe what I mean is that it's more compact. You get more like surface area between the grains. So maybe they move less, but they can move a tiny amount with more surface area. It's not fully known, right? So who knows? But this marble analogy, it's really helpful. It shows you how it kind of gives you like a qualitative idea of what's going on. But there's other theories. So, for example, other people believe the sounds produced by friction between sand that's been coated in dried salt. So similar to how when you use a violin bow, you coat it in this thing called a rosin. I think I'm pronouncing that right. Rosin, and that helps produce sound from violin strings. Similar to that, so I think maybe this sand coated salt helps, or there's another theory that proposes that you get these thin layers of gas trapped between all the sand grains, and they act as these percussive cushions capable of vibration, and they produce the tones that you hear when the singing sounds produced. And that could help explain why you actually need a tiny bit of humidity to help amplify the sound. Because if you have too much humidity, the sand grains stick. But if you have too less, um, maybe these percussive cushions, these little air pockets, don't form enough. So there's different theories, and it's no one. I had a quick look. I went and like Googled some papers, and there's a lot of papers related to this other phenomenon called singing sand. But squeaking sand is the one I'm talking about now, which I'm differentiating the two here, just to be clear. Some people do, some people don't. Um, but there doesn't seem to be like a nice qualitative model, or sorry, quantitative model that describes what causes what.
Um, Sorry, just to go back to the theory that it's trapped air that's being released between the grains that's acting as a percussive cushions. Not to be, I guess, immature about it, but so the sand is farting,
Could be
pretty much.
just like
It's just releasing gas and then causing like little vibrations similar to flatulence.
millimeter sized whoopee cushion.
There you go.
Who knows?
It also like, can we test it? Like we can't really test it in vacuum because we wouldn't be able to hear anything, right? Like how do you know if it's gonna be from air, or maybe if you put some kind of other type of fluid, does it squeak in like liquids, like that's not water, that doesn't make it stick?
Yeah, experimentally, I'm wondering how you could do this. Just like in terms of testing the salt, you could probably figure out ways in which you could remove salt from the surface through maybe some sort of polishing. But I'm just curious, like to really test this and understand these effects, which might be microscopic and harder to tell. Could you scale it up to, say, a bin of glass marbles and then just see if everything scales in the first place? Because you said this person from the YouTube video, used the analogy of glass marbles, but I'm wondering if you just made like a giant glass marble pit and then change the conditions there, because you could easily rule out with larger sizes whether it's air being pushed out, because there would of course be more room between the marbles, and so essentially more room for the air to escape without having that kind of percussive cushions. And then you can also test for saltiness and humidity too within the marbles themselves. But I am curious if this could scale up to larger scales, and what would need to be applied. Like, would you need a giant hydraulic press as the foot kind of thing to apply some sort of proportional pressure to the size of the marbles themselves?
Yeah, that's a really interesting way to go about it. I think so. It's maybe the sound comes from a combination of effects, and you could do this kind of analog system, this glass marble system that's scaled up, similar to how our recent guest Hamza, he studied grapes and microwaves to understand how infrared radiation travels in, or was it UV? It was infrared or UV radiation travels in microspheres, right? Like, I bet you could maybe do the same thing here, where you have these glass marbles, like you said, and then you could maybe come up with some kind of model, and then scale it down and see if it matches the data. And if it doesn't, then maybe there's something else going on, or maybe it's partially correct and it's missing something. So this is actually something I really like, this weird niche physics that, it's like it's not super important to understand how that works, but like we were saying, um, there's nothing wrong with just studying stuff to understand it, and you never know what applications it might have one day, right? So I think this is something I kind of want to look into, actually, as like a little side project. If any of you guys are interested in collaborating on that, I'm planning to go. There's a a squeaking sand beach in there's at least one on Prince Edward Island near kind of where I live. So I'm gonna visit there at some point, the near future, whenever I go home.
I'll have to check that out too. But in terms of interesting research, I mean, we have research relating to things like looking at the moon's regolith, which is just the sand on the moon, and how it's shaped and how it's formed and the effects it has on biotic and abiotic components, and also how it can be used, for example, for 3D printing. So maybe one day we can build a moon base on the moon using materials from the moon. So there's certainly a lot of interesting things that are being researched with sand. And again, I'm sure something like this could be very interesting. That's not realized yet. Again, it's kind of a curiosity at this point, but who knows? Maybe in 20 years, they're like, oh, yeah, this would be a great detector for such and such. Who knows? But I mean, I'm certainly down to help get it started. I just need about 1 million glass marbles and $100,000 in funding.
Yeah, I know people have studied it so far. Like, you can just take a microscope and look at the sand, and you can tell, like, oh, that it probably will happen here because the sand's very silica based and all same size. Um, but it's been a lot of like hobbyists, people who have been interested in it, who maybe don't necessarily have a big physics or like science background. Although like I said, there's a couple papers I was looking into. Maybe I found like 5 or 10 papers on singing sand, which is this related phenomenon that happens in sand dunes, which I am going to talk about one day, hopefully. Um, it's related, but slightly different. So, squeaking sand, I don't know if I found a paper particularly on it.
Well, the shape of the sand particles are not spheres. And well, I research shapes and crystals, right? And the thing is that might be a problem to try to modeling with spheres like marbles. So I think sands, the shapes come in all kind of shapes or form because this kind of macroscopic shapes rather than, let's say, the shape of a molecule or a bundle of molecules, right? So they come in higher shape of form. So when they got together, it's not like they gotta create this homogeneous thing. So you gotta be careful, try the modeling with spheres because if you put marble, like spherical marbles in a box, if you shake it and let it self-assemble, it's probably form either like face center cubic or hexagonal close packed. Probably H3P is probably the most common to see in like these spheres.
Yeah, it's a question of whether using spheres to model it is good or not. Like, does that tell you, is that what's happening, or is there more to it? So that's interesting, and that's something I want to look into one day, probably. So just as a last little comment, like, if you're ever at a beach and the sand kind of yells at you as you walk through it, that might be what's happening. If it's something else, then I'd be a little concerned, maybe. Uh, and there's a bunch of beaches you can find this phenomenon at if you're interested. Um, there's Where was it? There's a number of beaches in the British Isles. There's a number of beaches along North America's Atlantic coast. There's some other. There's actually a few beaches in the freshwater lakes of Lake Superior and Lake Michigan, and I'm sure there's more around the world. And it's most common at the certain parts of the beaches, the upper areas of the beaches. Sorry, I'm just reading my notes here because I wanted to comment on where, for people who are interested, where you might find it the most. The dry upper parts of the beach, the above the normal high tide line, but it can also happen in the lower area near the low tide line as well. but the key is a little bit of humidity, but not too much. So, if you're ankle deep in beach water, you're probably not going to hear it.
It's interesting that doesn't really happen on the Pacific coast of North America. Like, I'm just looking at a couple lists of where this happens, and none of them really mention Pacific coast in North America. So I think there's one in Australia. Not quite sure which coast that's in, but it's interesting that it's primarily the Atlantic.
I need citation need. I heard the one in Australia, that beach is like one of the bigger ones that has this squeaking sand. But it has to do the reason why you might not. I don't know. I didn't look at the exact location of the beaches, but if there is less on the Pacific coast, I think it has to do with like the formation of the shape of the continents and land masses and stuff. Um, in one of these YouTube videos I was watching on it, they were talking about how when particularly that beach at Australia, I think you meant the one I'm thinking of in Australia with that for that YouTube video I mentioned that the guy was at, that like somehow, glaciers ground up a bunch of rock and sand and silica and quartz, or maybe it was like land masses scraping together. I can't remember, but it's like a geological reason why only some areas have it and others don't.
Yeah, I guess that makes sense, especially if it requires something like quartz, then that's not found everywhere. So, yeah, definitely probably somewhere. Some places will have a higher quartz contents in their sandy beaches than others. But with that, thank you, Liam, for bringing that very interesting introduction topic. I think it had some very nice conversation. And if you are interested in funding this research, let us know by sending us an email, which we'll get into later. But moving on to our main topic today, something that's very relevant and kind of as you experience different parts of science and research, you start to see it everywhere. And it's this topic that we've actually touched on quite a bit throughout this show. And that's the interactions that occur between light and matter. Now, these interactions are happening constantly. I'm currently looking at a screen that is emitting light that has Feely and Liam on it. And even when you look, you're having light interact with matter. There's receptors in your eyeballs that are able to accept light and then send the signal to your brain. But also pretty much everywhere that you look, or even places that you can't look or can't see, there is light interacting with matter. So a really fun example is that when you pop a CD into a player to listen to an old album, and if you have not done that, talk to your nearest person that was born before the year 2000, you've experienced light interacting with matter in, I guess, more structured ways.
The other day, there's a grocery store near where I live, and they have this old video game store there. And I say old, but like, maybe you look inside and all the posters and games they're selling are from like when I was in high school and middle school. So not that old, but maybe old depending on how young you are. But anyway, it's been closed for the last few years. So every time I walk by, I'd look in and I'd get the blast of nostalgia whenever I go shopping for my groceries. And the other day I walked by and it reopened. And I was like, oh, I know there's a Left 4 Dead in there somewhere, one of my favorite games of all time. And what do you know? I went in and found one and bought it. So I've been playing Left 4 Dead a little bit the last few days. And it's on a CD. It's not, you can't get it digitally on an Xbox, right? So there's my light matter interaction story.
Exactly. So we rely on these. In some cases, they're more important than others, and I would say having a nostalgic video game is one of the more important ones.
I think so.
But yeah, these are all types of light matter interactions, and there's methods in which we can actually investigate these interactions, and this is kind of grouped into the general field known as spectroscopy. So before we delve into what spectroscopy actually is, let's discuss a little bit about how light interacts with matter, because there's a lot of ways in which it can interact with matter and how it interacts with matter, whether it's being emitted or absorbed by matter or transmitted through even. So just starting with the very basics, light itself is composed of photons, and these photons are elementary particles which carry the electromagnetic force. I'm sure we've talked about it in a previous episode about the 4 fundamental forces that we know of so far, and light or electromagnetism is one of them, and so we have light. Now, most of the light, or more so referred to it as electromagnetic radiation, or EMR, is at wavelengths we can't see. So photons themselves have an energy, and that energy can be described in terms of wavelength or frequency. I tend to like using wavelength just because it's a little bit more visual than saying, okay, how many times does it oscillate per second, instead saying, okay, how long is it peak to peak, which for me is a little bit more intuitive.
I'm a wavelength supremacist.
Heck yeah. There's dozens of us.
All 8 of us.
No. So just as an example of a wavelength of light that's emitted that you might have seen, again, not so much nowadays, but old street lights used to use sodium vapor. And when that's energized, it's able to emit photons at a wavelength of 589 nanometers. And if I remember correctly, there's actually 2 different types of photons that are emitted. We won't get into the details now. But they appear quite yellow, and so that's why, especially when you're flying over older cities or, we'll say, less developed cities, the streetlights might be yellow. Now, that's getting ahead of ourselves quite a little bit, but the important thing is that light is energy, and light is able to interact with matter and essentially convert energy from one form into another. So depending on the energy of the light, which we'll describe as the wavelength of the light to make this easier, it will interact with matter differently. So going back to that sodium vapor lamp, that yellow light, so at 589 nanometers, is produced when that sodium is energized, so electricity is pumped into it, and then the electrons within the sodium get excited, and then they lose that energy. But of course, conservation of energy doesn't let that energy just disappear. So when the electrons surrounding the sodium atoms go from one orbital, which is just one energy level, to a lower one, a different energy level, it will emit a photon whose wavelength is based on the energy that it takes to drop from one energy level to the other. So for sodium, when electrons move energy levels and they lose energy, that energy is not lost completely, it's just converted into a photon, which is released at 589 nanometers. And so we see that photons, like in sodium, or from the sun, for example, or from light bulbs, if you've got tungsten light bulbs in your house, then you're seeing the effects of electronic processes that are releasing photons. And I highlight seeing these effects because there's also other photons that are being released through different methods, but almost all the visible light that we're actually able to see is produced from electronic processes, and another process which we'll get into in a minute. Moving kind of into higher wavelengths, so infrared radiation, which is on the order of about a micrometer to tens of micrometers, that isn't so much produced from electronic interactions and emissions and absorptions of light. Instead, it's more so produced from molecules and the bonds that hold atoms together. So for example, if we look at carbon dioxide, there's a carbon connected to two oxygens on either side. It's a little bit not balanced, but essentially there are bonds between the oxygens and the carbon. And when those bonds start to vibrate, or when they start to jiggle, or even when the whole molecule starts to rotate, those correspond with different energy levels too, that are on the order of infrared photon wavelengths. And so, for example, something like carbon dioxide will be able to absorb and emit infrared radiation quite well.
But this is separate from the black body radiation, right? Because those are from kinetic temperature.
That's next. But yes, this is separate from black body radiation, where you have vibrational modes. So similar to how you have electrons that have certain orbitals, just because of the way in which the waves form at different energies, you have different vibrational modes for molecular bonds. So for example, A good way to picture that is for when you have a slinky, for example, and then you just kind of shake it willy-nilly. It doesn't do much, but when it's spread out between two people and you get it going at just the right rhythm, it produces this wave. So the same thing with the vibrational bonds, where they can only vibrate at certain frequencies, which correspond to the energies. So really interesting thing about carbon dioxide is, again, it's able to absorb that infrared radiation, especially if it's being reflected from the surface of the Earth. And then it re-emits that radiation. So it gains a little bit of energy, starts vibrating, and then that vibration stops. Energy is converted back into a photon, and that can be re-emitted in any direction. So there's a chance it's re-emitted back towards the Earth. So the more carbon dioxide, the more reflection. But you've heard that before. So touching on what Feely said, and if Feely wants to add to this, feel free. But the other way in which light can be produced is not just limited to molecules and atomic processes, but one of the main ways is that when many of these atomic or subatomic components are combined together and moving together in a kind of macroscopic object, they create what are known as a black body. And this produces black body radiation that any object with the temperature will emit. So something, for example, like the sun, which isn't quite a black body, but we can kind of compare the spectrum released by the sun and the intensity at each wavelength, or the number of photons that are released, to a black body. We also see this when things get hot. So if you have a stove right now in your house, go turn on one of the burners, provided it's not one of those induction stoves, or a gas stove, I guess, and you'll start to see it heat up. And as it heats up, it will start to glow red, and then hopefully it doesn't turn white, but very well could. So this is black body radiation, which is a different method for how light can be created from matter. And then black bodies, a perfect black body will absorb all radiation as well, but of course that will give it temperature, so it will emit. So even your body itself is emitting some sort of radiation, but it's a lot lower, a lot larger wavelength, lower frequency in the thermal infrared region.
Yeah, I think this is a concept behind the idea that black holes can lose energy, right? Before the idea of black body radiations, like black hole just sucks in everything. It's like perfect black body, but now we know that's not true, right? The black holes still have a chance of decay or Hawking radiation that emits out. Liam, does black hole emit black body radiation?
Well, we think so. We've never seen it because the cosmic microwave background is way warmer. It washes it out. But yeah, the black hole, and by definition, it is the perfect black body. It's the perfect absorber and perfect emitter of thermal radiation.
Just to sidetrack a little bit, isn't it that a black hole doesn't emit photons themselves, but it's through the mechanism of Hawking radiation that's able to release energy? Or does it actually release super low energy photons?
Well, it has a Planck spectrum, a black body spectrum. It releases very long wavelength photons given exactly by a Planck spectrum. Depends who you ask, but that's the commonly accepted thing. So that's what Hawking did. He went and derived that it's actually just straight up a black body. The photons aren't coming out of the black hole, but they're appearing near its edge, and they're somehow carrying energy away from the black hole because you get two of them produced, and one of them has to be a negative energy one that goes into the black hole. It's kind of a little bit unrelated to the spectroscopy, at least what we're going to talk about today. But yeah, it's a black body. At least we think it is, and then there's many other theories that modify that and go beyond it. So we better not talk about those.
Yeah, definitely for another day. But so we do have black body radiation as well. So when we have light interacting with matter, the main things that it can do are be emitted from the matter. It can also be absorbed by the matter. So for the emission, we see that in whatever light source you're looking at, whether it be the sun, don't look directly at the sun, or a light bulb. For the absorption, you'll see that if you're wearing any type of colored clothing under white light, then you'll see only the reflected light. So, for example, I think Liam's wearing a blue shirt right now.
It's gray, but it's hard to tell
Oh,
with
it's
the
gray.
camera
Okay.
and my bad lighting in my living room.
Exactly. But some light is being absorbed by that, some light's being reflected, and probably a little bit more blue light, at least according to the camera. And then light can also be transmitted through an object. So something like glass. And there was a really interesting video I watched not too long ago. The main topic escapes me, but the fact was stated that we have technology to produce so pure of glass that if it were, oh, I forget the scale of it, but if it were as deep as the sea, you wouldn't be able to tell that there was glass there. So if you had this very well manufactured pane of glass that extended all the way down to the bottom of the Marianas Trench and the Challenger Deep, there wouldn't be any discoloration like what you see with panes of glass where it looks green.
Well, let's look at this. A little bit of admission. How many times have we run into a glass panel? I thought it was a door. Yeah, I did it a few times. Cause in my old place back home, we had like the glass panel for the balcony, like the glass door. And sometimes I just hit it, and my mother just put like stickers on it, so we know that yes, this is glass, is closed. I mean, we can't even tell when it's transparent.
My my again unrelated to spectroscopy, but my way back in the day, my grandparents, my grandmother, she kept a clean house. Like everything was cleaned and polished, and the windows were super clean. So there was a deer out in the yard, and my grandfather went because deer are pests where I'm from. It's funny because you tell people like, "Oh, we hate deer," and they're like, "No, we love deer." I mean, I don't hate deer; they're cute, they're fun, but they're everywhere and they carry ticks that have Lyme disease, so people tend to not want them in their front yard. But there's a deer outside, so he like got his gun and he went to shoot it, and he shot straight through the window because he thought the window was open because it was so clean. He didn't realize the glass was there, so he blew the window open trying to get the deer. And so that's a funny little story related to clean glass. But what you were saying, Patrick, on this, you could have like the glass as deep as the ocean, and you wouldn't be able to tell that it was there. But surely, like when obviously that's not practical, but like this very high, I don't want to say high purity, but this very like clean, nice glass, like surely it's quite expensive to make it that pure, and I don't know. Like
I mean, it is absolutely expensive, but you were just experiencing issues with this type of glass, which is fiber optics. I mean, fiber optics have to be incredibly well manufactured. They are expensive, but light's able to travel through it uninterrupted for many, many kilometers.
yeah, people won't know I was experiencing issues with fiber optics because Feely will edit out the fact my internet cut out halfway through this recording.
Mhm.
And now the truth is revealed.
Hopefully it doesn't happen again before we finish.
Absolutely. Yeah, so the main ways in which light can interact with matter is it's just transmitted straight through, which in itself could depending on who you ask, it's a form of transmission or absorption and transmission that just kind of continues on. But depending on who you
I
ask,
disagree.
where we also have reflectance as well from objects. So talking about Liam's shirt again, and the color that's perceived is some of that light is absorbed, some of it is reflected, which again could be argued to be absorbed and then just re-emitted. But again, depends who you ask, and don't
Well, there's
follow Ian.
there's like a good YouTube video. I don't remember the name of it, but it talks about why the speed of sound, or not speed of sound, the speed of light changes in different medium. And it basically makes an argument as to why the absorption and re-emission uh like theory is just bad. It doesn't work, right? It has to do with it's waves. You have to treat the latest waves, and you get interference, and then you get a new wave that moves slower. So anyway, at least for that, I think the reabsorption and emission not right.
I feel like that was a 3 blue, 1 brown video, but
Probably.
if we can find it, we'll link it down below.
Oh, just use ray theory, bro.
Well, you can't use ray theory when you're working on when the wavelength of your light is about the same size as the things it's interacting with, because then you get diffraction.
And that's something that I kind of wanted to bring up is we've been talking a lot about visible light and infrared light and also very, very long wavelengths of light. Whereas, like, for example, you can have light interacting with matter in the radio wave or microwave region, but we see the different effects. So we kind of talked about microwaves here and in our episode with Hamza, and even radio waves, they will reflect off large objects. So we have radar satellites that are able to detect objects on Earth, but they're limited in the wavelength. So a radio wave that's emitted and received that's a couple meters in wavelength wouldn't interact with something like a mouse because it's not on the same kind of order of magnitude to actually interact and reflect and be detected by something. And then we also have X-rays and gamma rays, which are also photons of light, but they tend to be produced through other methods. So X-rays, for example, are produced commonly through something called Bremsstrahlung, which is just the acceleration, whether it's the acceleration or deceleration, same thing anyway, of electrons. And then you even have gamma rays that are produced from nuclear reactions and nuclear decay. So there are other ways in which photons are produced and interact with matter, but they're also useful in the field of spectroscopy because it's just such a wide-ranging field. Even just going through the Wikipedia article, I mean, the applications are endless for spectroscopy. And the really nice thing is that we have, at least in our current day and age, a good understanding, whether theoretically or experimentally and through observations, of how different molecules and different atoms and different wavelengths of light all interact with each other. So there's a lot that can be told from spectroscopy. So kind of transitioning into the second part of the main topic, I want to talk about some uses of spectroscopy. I know Liam has stated that it's not something he's been too familiar with or has used, which, I mean, you can't blame him for being a theory guy.
Yeah, I mean, all the experimentalists use it because anytime you have light and matter interacting, you kind of need it to see what you're doing. I was traumatized because I'm not going to get into the details, but in our undergraduate degree, we had a lab in a modern physics class, and we had a spectroscopy lab, and it was a rough one for me and my partner. I'll just leave it at that. I did not have a good experience, and anyway, it's super interesting. It's really cool. I wish I could, go learn more about it if I had more time. But yeah,
Absolutely. But I mean, spectroscopy, it is everywhere. It's even in something like my current research where I'm looking at how light is reflected from the sun on the surface of the earth and detected by different sensors, and understanding how the spectral reflectance from the surface of the earth can tell us about what is contained there, whether it's as roughly grained as, okay, here's water, here's not water, versus like here's one type of tree versus another type of tree, or one type of rock versus another type of rock. So there's even in the field of remote sensing and earth observation, spectroscopy is huge.
yeah. Does it all? Tell me if I'm wrong, but I think it all like boils down to the fact that, like you said, I think you might have mentioned it, but certain elements emit certain wavelengths of light. So if you point your telescope in some direction or your microscope at some element, you don't know what it is. You can look at these specific like wavelengths that it emits. Even if it emits different ones of light, you can do these fancy Fourier transforms, and you can decompose the light that you see into various frequencies. You can tell like, all right, this element that we see is made up of this wavelength and this wavelength and this wavelength and this combination, and that's a signature of some kind of, I don't know, like hydrogen gas or something else more complicated. So I know a lot of astronomers where I work, right? They point their telescopes in the sky and they look at all these gas nebula and different galaxies, and they can like look at the light that comes from them and say like, based on the colors and the frequencies or the wavelengths that we see, we can estimate that 80% is made out of helium or whatever. I don't know the elements, but
Uh, I I'm glad you know hydrogen and
Those are
helium. But that is
as a theorist, those are the only two things I know.
oh boy, I'm surprised you know
I know
helium.
rubidium because they make BECs out of that, but
There you go. But that is one application I want to touch on is in space. A lot of observation involves spectroscopy. So we heard in last week's story that it required a spectrometer to discover dark matter, whereas we've even had a friend who has done research trying to do spectroscopy on interstellar gases that exist between the stars. And so they were able to look at light coming from suns that are passing through different clouds of interstellar gases and then working through, like you said, kind of Fourier transforms and other advanced types of analysis to understand what those gases were composed of. And I believe it ended up being like extremely long carbon molecules where there were 40 or 50 or 60 carbon molecules within these gases. So that in itself is very cool and requires spectroscopy to understand, okay, where is light being absorbed and where is it being transmitted through these gases? And we can even go a step further, especially with the James Webb Space Telescope, in which it's able to look at exoplanets as they pass in front of their sun and then see what light or what electromagnetic radiation is transmitted through the atmosphere of those planets to understand the composition of the atmospheres of these planets that aren't even in our solar system. And reading that for the first time a little while ago, it was just mind blowing.
yeah, that's a pretty common one, right? But it's kind of like whoever came up with that was quite smart. It's a very clever way to be able to tell what's in a planet's atmosphere, with even though you're could be light years away.
Yeah. I mean, the uses in astronomy are endless, let alone what we can do in a lab. So I do just want to mention a cool research project that was done by myself, and it was worked on in parts through different people that passed through our undergraduate university. But it was looking at how we could measure the global warming potential of different molecules, especially very complex fluorocarbons, by shooting a laser that varied in wavelength and or frequency, we'll say, and by passing it through a bunch of mirrors before recording the end result of the intensity of the laser, we could figure out how much light was absorbed by these molecules, and then figure out how much of an effect they would have for their greenhouse gas potential or coefficient. So that was another use of spectroscopy that combined physics really closely with some environmental research, and as well as chemistry too, because chemistry depends a lot on spectroscopy to figure out, okay, we're looking at something, not quite sure what it is, but you can do spectroscopy, also X-ray diffraction and things like that to figure out what exactly you're looking at. Spectroscopy can also be used to understand things like nuclear decays that are occurring. So when we're looking at background radiation, for example, like what we talked about kind of in our last episode with John, we are interested in understanding what energies are being produced and what products are being produced from different nuclear decays. And so when we're looking at something like gamma radiation, we can figure out exactly what process occurred, what kind of decay occurred, and what specific elements and isotopes were involved in that by examining this spectroscopy of these gamma particles.
It's almost like light is the main thing that we have, right? Because what other mechanism do we have? We can do it by sound, or basically just mechanical energy, really, or have some kind of mechanical, like kinetic detection. So the rest they're all difficult. Light is, in a sense, the easy one, but also the hard one, because it's almost the only thing we have, especially if you look at astronomy. All we have is light. The rest we cannot get. And when you look at something really small too, we had an episode with Kat that they do atomic force microscopy, right? They use that's difficult to do. but the things that they already have is light, or we can induce something for them to create light or electromagnetism. The rest, you think of auto force, gravity. Yeah, well, a lot of things are low mass or really high mass, kind of hard to get, and it's tapered off. The magnitude of the force taper off really quickly. It doesn't travel that well. Like it took us so long to build a gravitational wave facility, right? And strong and weak nuclear interactions. Good luck. Like people who try to fight dark matter with weak, it's really difficult. So the only thing that we really have left is either like mechanical stuff, kinetic, or light.
Yeah, and I mean, I can speak that there are dark matter detectors that try and use, uh, I wouldn't say quite acoustic, but like phonon or even the bubble creation chambers. But yeah, I mean, light's incredible, and it only is emitted by something like 4% of the mass of our universe. So it's useful to us, but how useful is it in the long run? And
Well, when you say something is like that, it sounds like little, right? But if you look at how much of mass occupied space in the universe, it's like really small percentage too. Like the thing that we experience are mostly just the very few, very small percentage of the universe. But I don't think it's that meaningless. I think there's a lot of things in the 4%, like the 96% that doesn't interact with light. That's very difficult. Well, I think if you look at mass wise, it might be true, but if you look at things that we interact with, that 4% is almost the 99% of what we interact with is the 4%.
I mean, I'm still rooting for entire civilizations being built from dark matter and dark stars and dark planets, but that's besides the point. Anyway, I think in the interest of time, we'll end our main topic here. If there are any final comments, I will say mass spectrometers exist, but no way we're getting into that today. Okay, so before we get into our story today, I'll just let you know how you can reach us. If you have any questions, if you have any ideas about future episodes, or if you'd like to fund our experiment to figure out why sand barks, regardless of how you want to reach out to us, you can reach out to us through email. We are hyperthesispodcast@gmail.com. You can send us an email anytime. We're pretty good to take a look at the email pretty frequently, and we're more than happy to receive requests for episode ideas, or if you are an expert in your field, we would love to hear from you and have you on the show. If you are a little bit more email adverse, you can find us on Instagram. We are at the Hyperthesis on Instagram, so you can give us a follow there. You can like our posts. We do post updates for every episode that we put out, along with just some other fun updates and behind the scenes looks. We also check our DMs on there, so you can send us a DM as well. Again, if you are an expert in your field, or if you have suggestions, questions, comments, concerns, queries, whatever other word you can think of to reach out to us. If you're listening to us, congratulations, you found us. We are pretty much on any podcasting service that you can find. So we're based out of Spotify, but we're on YouTube Music, Apple Podcast, Audible, wherever you find your podcasts. So if you have the option in your podcasting app or podcasting service, feel free to leave us a review and a rating. Leave some comments too. We check those as well to see if there are any suggestions or ways in which we can improve your listening experience. And I'll see if Feely can do like a fun little edit for there to make it super smooth. Anyway, we are also on YouTube. You can find our previous seasons all updated on YouTube. You can also leave comments, like, subscribe, whatever you like to do there. But go check us out. I've been so tempted recently to start posting shorts because there's been like sundogs because it was -40, and then just a bunch of other things that have gone on that are interesting. So maybe if you subscribe there, I'll start posting stuff. Regardless of how you want to reach out to us, please feel free to reach out to us in any way that you prefer. Share us, like, subscribe, leave a rating, leave a comment, whatever you need to do. And again, if you're an expert in your field, we would love to have you on the show, kind of pick your brain and figure out why you do what you do and what you do. Anyway, uh, reach out to us however you like, and thanks for listening. Now, to end today's episode, we will finish with a story from Feely.
Well, today's story is about Lord Rayleigh. As you might know from Rayleigh's Scattering, which explained why the sky is blue, it's the first work that correctly explained why the sky is blue. So, Rayleigh is not his birth name because he was the Lord of Rayleigh, is the inherited name. So his name was John William Strutt, where his father was born as the second Baron of the Baron Rayleigh of Tearing Place in Witham in the county of Essex in England. So the family had little interest in science because they were landowners with interest in the country. So he didn't really succeed the title until he was 30 years old. So Rayleigh, when he was a boy, he suffered from poor health. So schooling was difficult. He had to leave schools after a short period because health. So 4 years he spent at Reverend Warner's boarding school. So that prepared him for university. And he didn't really show any sign of mathematical genius or such. So during these 4 years, he has tutors and such, but he didn't really show any sign of that he was more than just an average student. Then he entered Trinity College in Cambridge in October 1861, and he went into mathematics. He took the mathematical honors exam called the Tripos. His coach at Cambridge was actually Edward Routh, who apparently was the most famous Cambridge coaches, perhaps all time. And he was also an applied mathematician, which works on dynamics. It was more than mathematics that he learned. He also learned how to apply mathematical methods to tackle problems. Another influence that Rayleigh had in his undergraduate years was Stokes, as you might know from Navier-Stokes from fluid mechanics, who was a professor of mathematics at the time. So Stokes inspired Rayleigh with the lectures, which combine theory and practice in a different way, that with many physical experiments being carried out during lectures. Because back in the days, undergraduate students were not allowed to do experiment. So it showed Rayleigh that the actual experiment. So he was not a typical student because he actually was awarded an astronomy scholarship in 1864. And in the honors exam of 1865, he was awarded senior wrangler. So basically the top first class student. And in the same year, he was the first Smith Prizeman. Knowing that he would gonna become the third Baron Rayleigh, so being scientist was really not acceptable because the family didn't feel like, well, science was worthwhile more than succeeding the title and become the Baron. So, but Rayleigh at the time was determined to devote his life to science, and he's not gonna back down. So in 1865, after reading Maxwell's paper on electromagnetic theory, and also he studied deeply with Helmholtz, who at the time worked on acoustic resonators. So he's gonna publish his first paper to make his mark in science. And in 1866, he was elected to be a fellow of Trinity College in Cambridge. So at the time, usually scientists would tour Europe to gain more knowledge and such to get better. But he went to the United States and he kind of used his privileged position so that he didn't really need an academic post for money. So when he returned from the States, he purchased equipment to do experimental research by himself and set it up on the family estate. So make no mistake, Rayleigh was actually famous for using cheap equipment, not expensive one. He was quite economical. And so Rayleigh's theory of scattering was published in 1871 and it was the very first correct explanation as to why the sky is blue. And in the same year, he got married. However, after he got married, he had an attack of rheumatic fever, which almost ended everything. So then he was advised to travel to Egypt. So and he did with his wife. So they went through the Niles in the last month of 1872 up to 1873, and returned to England in the spring. It was during the trip he actually recovered his health, and he wrote the text, the theory of sound, while on the trip. And these are the couple volumes of famous books. Because the first volume was about vibrating mediums that produces sound, and it was published in 1877. The second volume is about acoustic wave propagation, how wave propagates to the medium, basically, and was published the next year. So after his trip from the Nile, Rayleigh's father died. He succeeded at the title to become the third Baron Rayleigh, and then he continued to work in the family estate. And from 1879, a couple years later, to 1884, he was the second Cavendish Professor of Experimental Physics at Cambridge. The laboratory was opened 5 years earlier, and the first Cavendish professor was Maxwell. So one of the most important pieces of experimental work as a professor at the time was he standardized the ohm, or the unit of the resistance, and what is 1 ohm. So Maxwell and Crystal had carried out the experiments before, but so the apparatus was still available for Rayleigh. However, he needed to build a new one because it wasn't enough to obtain the required accuracy. And in 1884, he resigned from Cambridge to return to do research at his own estate. And his financial position had improved, and he really loved scientific research. So that he doesn't really need to do university posts, don't have to teach, just do research. And many colleagues try to get him to reconsider this and become the chair, but he really just want to do research. Even though he make frequent visits to London, where we talk to scientific societies, still mingling with scientists to really collaborate with them. So Rayleigh is actually most famous for his discovery of argon, which is an inert gas, in 1895, which earned him a Nobel Prize in 1904. And in 1908, he accepted the post of the Chancellor of the University of Cambridge, and retaining this position until he died. Even to the end, he worked on scientific papers until 5 days before he died on June 30th, 1919. Well, that's the story of Lord Rayleigh, which I didn't know wasn't his name. It was a title, which is kind of funny. Well, I hope you guys enjoy.
Well, thank you for the very interesting story, Feely. That was really enjoyable, and thank you for sharing. And thank you all for joining us today. See you in the next episode. Bye, everyone.
We'll see you later. Take care.
Thanks for the story, Felix. Bye, everybody.